In continuation to the dielectrics, so where we are going to use this dielectric, basically we study about the dielectrics because we are going to use it in the capacitors. How we can use it in the capacitor? We are going to place this dielectric material in between the capacitor parallel plates, right? So we are going to find out what is the parallel derivation for capacitance of a parallel plate capacitor with dielectric. Okay, coming to the topic. See here, so we would have already discussed about this dielectric material in the previous session. So in this case, I have taken a positively charged plate and a negatively charged plate separated by displacement of d. Now I am going to place this dielectric material in between this parallel plate capacitor, which is having a charge density here, charges minus qp at the one end and plus qp at the other end. Kindly notice the diagram here. The positive charged plates are having negative charges in the dielectric nearer to it, and the negative charged parallel plate has the positive charge of the dielectric nearer to it. Why? Because of attraction, obviously. Now the electric field in between the parallel plate capacitor will start from positive charge and end at negative charges, obviously. So that is taken as E naught here. So there are some induced charges in between the inside the dielectrics, and the electric field due to that induced charges is going to be EP, which is nothing but electric field due to the polarized charges. Now the resultant electric field is taken as E here, right? So I have already told you about rules for calculating the capacitance. So first what we have to do, we have to charge the capacitor, get some electric field out of it, and we have to find out the potential using electric field or potential gradient equation. And then what we have to do, we have to find out the capacitance by using the equation. So now see here, so I have taken Q and minus Q as the charges given to the plate, QP and minus QP as the induced charges on the two faces of the electric slab, and E naught is going to be the applied field, EP is going to be field due to polarization, E is going to be the resultant field. So now I know what is going to be the electric field between the parallel plate capacitor is already derived by using Gauss law, and we have already noticed that E naught is going to be sigma by epsilon naught, and sigma is nothing but charge density. So Q by A, if I substitute, I will get this equation. So Q by A epsilon naught. Next, according to the general equation for dielectric constant, I have already given you the equation. So E is going to be E naught by K, which is nothing but the drop in the electric field is due to the the dielectric constant of the material. So it is going to be E naught by K, so which is equal to, I have already derived E naught, so I am going to just substitute that here. So Q by epsilon naught A into K is going to be that. Now according to the equation of potential gradient, so V is equal to E into D, where D is going to be the displacement between the parallel plate capacitor, and it is again the thickness of the dielectric material which is used inside, right? So now V is equal to, I have already found out the electric field, so Q by epsilon naught A into K, I am just substituting it and multiplying it with D. So now I have got the potential, I know what is the electric field, and based on this potential equation I can derive capacitance. So C is equal to Q by V. So Q is nothing but the same, V is going to be Q by epsilon naught AK into D. So now if I substitute the equation here, then QQ will get cancelled and epsilon naught AK, so I will get C is equal to epsilon naught AK by D. So can you find out the difference between the normal capacitance and the capacitance with the dielectric medium? Yes. So normal capacitance will have epsilon naught A by D alone, but now since I have a dielectric medium in between, I am just multiplying its dielectric constant here. So I will get the capacitance for a capacitor with dielectrics. So the entire equation now turns like C is equal to K C naught. C naught is nothing but the capacitance without a dielectric, which is general capacitor. So air core capacitor or vacuum core capacitor, epsilon naught A by D. I am just substituting it so that I can find out its law. So if a question is asked like find out the capacitance of a parallel plate capacitor if a dielectric medium is placed in between them, if its capacitance value is given without having any dielectrics, then I can use this equation to find out the capacitance with the dielectrics. Okay, so that is what we are that is why we are deriving this equation. Now, so according to this equation, we can write a statement like the capacitance of a capacitor is increased by a factor of K. Yes, so when I introduce some dielectric material in between the parallel plate capacitor, its capacitance value increases because it is multiplied here. Yes, so the factor of K, where the space between them, between the plates is filled with the dielectric of dielectric constant K. So we can define dielectric constant by this definition as well. Okay, so this is all about the parallel plate capacitor with dielectric material. Now we can also find out the magnitude of the induced charge which is present inside the dielectric when I am passing some electric field inside. Yes, so initially the applied electric field is taken as E naught is equal to Q by A into epsilon naught, and the polarized electric field sigma P by epsilon naught, which is equal to QP by A into epsilon naught. Yes, the induced charge density is generally taken as QP by A. Now when it is substituted in electric field due to the induced charges, so QP by A into epsilon naught is taken. Now the electric field, the resultant electric field is nothing but E naught minus EP. Why? Because the applied electric field is opposite to that of the induced electric field. So E naught minus EP. So just substituting the equations here. So Q by epsilon naught minus QP by epsilon naught, I'll get E is equal to Q minus, so denominator same, so I can just subtract it. So now from the equation E is equal to Q by epsilon naught A into K. So if I am substituting that equation here, right? So what happens? So electric field on both the equations, left hand side is same. So can I just equate the right hand sides? So Q minus QP by epsilon naught A is equal to Q by epsilon naught A into K. Yes, so epsilon naught A gets cancelled. So Q minus QP is equal to Q by K. So from this, can I find what is QP? Yes, I'll get QP is equal to Q minus Q by K, where Q is taken commonly out. I'll get 1 minus 1 by K. So this is how the magnitude of induced charges is derived. Now we have a question here stating that a parallel plate capacitor has plate area A and plate separation D. The space between the plates is filled up to a thickness T with the dielectric of dielectric constant K. Calculate the capacitance of the system. Simple here. So what we are going to do is, we have a parallel plate capacitor and its plate area and the separation is given, and there is a space between them where it is filled with the dielectric material with a thickness of T, which is very much less than D, which is nothing but it is somewhere in between the, or the thickness of the dielectric material is less than the spacing. So we are going to calculate its capacitance. So now see the diagram here. So I have already pre-drawn it. So I have two parallel plates where it is going to be A and B, and it is separated by distance of D. As per the question, I have a dielectric material in between where I have stated it as C and its thickness is given as T. Right? So initially two conditions here. There is a capacitor here and there is a capacitor here. So now the capacitance of a capacitor between A and C. So what is the capacitance between A and C is calculated. So it is calculated as K into epsilon naught A by T. So T is going to be the thickness of the materials here, and K is going to be the dielectric constant. So K epsilon naught A by T is given as C1, which is nothing but the capacitance between A and C. Now next is to find out the capacitance between B and C, or C and B, whatever may be. So the capacitance in between them is considered to be this one. See, in this, the spacing between B and C is taken as D minus T. Why? Because the entire displacement is D and there is some thickness of a material which is already taken into consideration. So the left out displacement is going to be D minus T. So that is what is taken as the displacement between B and C. Now the capacitance between these two is going to be epsilon naught A by D minus T. Why are we not taking K here? Because there is no dielectric between them. There is only air or vacuum, whichever we have considered it in a general equation. So I have just taken C2 is as epsilon naught A by D minus T. Now what is the equivalent capacitance? Is going to be acting as a series combination. So one or the other is going to continue. So the tail of the capacitor is getting connected to the head of the other one. So there is going to be a series combination. The equivalent capacitance considering series combination is going to be C1 C2 divided by C1 plus C2. Now we have already calculated what is C1 and C2. So just substitute that here and the other parameters gets cancelled and taking the LCM out. So if I take the LCM and epsilon naught A is common here, so I am just taking epsilon naught A common here and I am just cancelling here each and every thing which is same on the numerator and denominator. Now we are arriving with an equation K epsilon naught A divided by K into D minus T plus T. Further simplifying, I get the capacitance of a parallel plate capacitor with the dielectric medium with the thickness T as C is equal to K epsilon naught A divided by K D minus T into K minus 1. So this is what is the capacitance for a capacitor which has some dielectric with the thickness of T in between the parallel plates. Next is the energy in the electric field in a dielectric. Okay, so it is very similar to that we have found out already as the energy in an energy stored in a parallel plate capacitor. The only difference is the dielectric is going to be placed in between the parallel plates, and we are going to find out what is the energy stored in the dielectric material or the energy stored in the capacitance of a parallel plate capacitor or the energy stored in the capacitor, right, with the dielectric. Now initially it is going to be the potential energy or the energy per unit volume. So U is going to be U by V. So we have already derived all those stuffs here, and the volume is taken as A into D, area into the displacement. So this is going to be the diagram, considering the same diagram here. And now U is equal to half CV square. Now I know what is the capacitance of a capacitor whenever a dielectric medium is placed in between. It is nothing but K epsilon naught A by D. So half CV square, and then substituting the C value in between in that, then we get this equation for potential energy. Now potential energy per unit volume is given as U is equal to half K epsilon naught A by D into V square divided by its volume. So A gets cancelled, and I will have U is equal to half K epsilon naught V square by D square. So now I'm just taking all these common, because we know V by D is going to be electric field. So in order to know what is the energy stored in the form of electric field in a capacitor with the dielectric only is derived here. So I'm just making this V by D as E. So now what I'll get, half K epsilon naught E square. So this is nothing but the energy stored in a capacitor per unit volume. So just related with the equation which we have already derived for a energy stored in a capacitor, so we in terms of electric field, so we would have derived it as half epsilon naught E square. So just correlating these two equations, we can easily find the only difference is going to be the dielectric material or the dielectric constant in between the parallel plates. So that's all for this derivation. So we have found out the energy stored in an capacitor in the form of electric field with a dielectric between them.